I believe this is lesson set 7, if I'm not mistaken. And we'll develop some mechanics, and over time, concept will follow. So I'm introducing the derivative of the tangent function, which we'll do mechanically here using the quotient rule. Sine over cosine, another way of writing tan, so we're going to do y prime here. Low, d high, derivative of sine, cosine, minus high, sine x, derivative of cosine, d low, minus sine x, over low, low, squaring the denominator. Okay, now that too, I could have shown it as squaring the denominator that way, but getting rid of the parentheses and putting the 2 there is 2 fewer strokes of the pen. So probably a shortcut happened, who knows when, but got adopted. That's my guess. And so we got cosine squared plus sine squared coming out of the numerator, and sine squared plus cosine squared is 1. So we got 1 over cosine squared and 1 over cosine secant, so we got secant squared x, and you need to memorize it. A lot of memorization in calculus. Okay? So get your cheat sheet, have it handy. Each time you see a function, look at the derivation. All right, so secant squared x. So now we'll do a bunch of just mechanical problems and have a little quick practice here. So we can now use, all of these are going to be y equal statements. All right, and I think I started it and then I had to stop because I couldn't remember what 3 to the 1.001 was. And I did it out because I wanted to write it down, and now I don't have a calculator and I'm not going to be able to do that one in my head. But it proved the exponential differentiation. All right, so if y equals 3 to the x, then y is equal to the ln of the base, which in this case is ln of 3, times 3 to the x. So I decided to put a 1 in for x, and I got 3, and then I put 1.001, and I can't remember it now. But it did come out with the rate of change of 3 to the x at x equals 1 from a numerical standpoint, which is 1.1. Or maybe I did 0. 3 to the 0 is 1, and then 3 to the 3 to the 0, 0.001 gave me that number, and then y2 minus y1 over x2 minus x1 gave me a correct numerical result, because the ln of 3 is approximately 1.1, and 3 to the 0 is 1, and the numerics worked out just with 3 decimal place accuracy quite well. All right, so that's the exponential differentiation. The y equals b to the x, then the derivative is ln of b times b to the x. So what's the derivative of 3 to the x? So we're going to do low first, low, tangent of 5x times high, minus low d high minus high, d low, and now it's time to take the derivative of the tan of 5x, which is going to require the chain rule. So it's secant squared of 5x times 5. That's just mechanics. And now we have tan squared of 5x in the denominator. And you don't have to simplify or do any algebra with working calculus. It's basically, when you're tested, it's can you write the correct statements. Okay, so there's problem number 1. Now I've got a little room for problem number 2, which was done last week. Do you recognize it now? I hope so. So what is minus x over 3 plus pi? It's just a linear function, and the derivative of a linear function is the slope itself. So y prime in this case is equal to minus 1/3. And we talked about that a couple of days ago. Okay, pi, not a variable, represents a number. Okay, and that number is not changing. Well, irrational, that's kind of an awkward thing to talk about. But let's move on. Product rule, e to the 2x times sine 3x. So that means you're getting a little repetition on, do you remember what the product rule is? Product rule coming from length times width, talked about it on Friday. L prime, when it changes a little bit, times that distance, and then we got a little change, especially if this is a function, and that side. So derivative of e to the 3x, we'll do that one. 2x, I think it's a 2 here. E to the 2x becomes itself times 2, but we'll put the 2 in front. Leave sine of 3x alone. Plus then the derivative of the sine function, which is cosine of 3x times 3. So 3 cosine of 3x. And leave the first one alone. Okay, and there's your product rule. And you can go to the playlist and see this done out from a conceptual standpoint and mechanical standpoint and numerical standpoint. And then maybe you'll trust the formula a little bit more. Okay, so you do have homework, I guess a little bit of homework on your part, because to keep these videos down to a manageable, let's do it every day, I can't go off on too many tangents. Calculus is all about tangents, so maybe I should go off to tangents. But anyway, another chain rule problem right here. So if y equals sine of, so there's the 7th power, the sine of, e to the, and the square root of x. There's 4 functions involved here. So I think there's going to be 4 lengths. So the first thing we do is take the derivative of the outside function, which is 7 times something to the 6th. And what is that something? I guess I've got to start this higher and start up here. So we got y prime is equal to 7th of something to the 6th. I decided to write it that way this time. E to the square root of x. Derivative of the sine is the cosine function with respect to where you are on the x-axis. I do have a chain rule through the lens of integration video. It's a little heavy. You might have to see it several times before it makes any sense. But it does, I think, address where's the chain rule coming from. At least that's my interpretation. So I just did the derivative of sine is cosine with respect to where I am. Now I got to do e with respect to where I am. So I've got e times the square root of x. And now I also have the derivative of the square root of x, which I've asked you to memorize as 1 over 2 times the square root of x. I'll do it one more time here, x to the 1/2. So if I take that derivative, I multiply and drop down by 1. The negative means I have 1/2 times x to the 1/2. And what does that 1/2 represent? The square root of x. Now I just butchered something here with the 1/2. Okay, so let's do that again. So I've got 1/2, right? I'll write it that way this time, times x to the minus 1/2. That's what puts this in the denominator. Okay? And so much easier to work with this than the power. All right, so did I finish it? Yes. All right, so when you get good at these, you just write those quickly. It becomes a 10-second problem. All right, so now we have 1 over x, and I put that there because you're going to work with 1 over x so much that it's easy to make a mistake. You look at 1 over x, and the integral of 1 over x is the ln of x plus c. Okay, and it's just really easy to do that, but I'm not asking for integration here. I'm saying take a derivative. So you have to rewrite 1 over x as x to the minus 1. Okay, now you can use the power rule, so we have minus x to the minus 2. Which is the same thing as 1 over x squared, just to get a little algebra review for anybody who may not have integrated that concept and mechanics along the way. Doesn't mean you can't. Okay? So the derivative of 1 over x is minus 1 over x squared. Okay, so I've corrected it, so I can erase it now. All right, next problem. Cube root of x to the 5th. So the cube root of x to the 5th, I'm hoping, with the little practice we've done, that you have x to the 5/3. It's another way of writing this. And so now we're going to multiply by 5/3, and we're going to drop it down 1, which is basically subtracting 3/3, right? Okay. And now we did this one on Friday, a couple of days ago. Let's do it again. So what is P prime? P prime is the derivative. I don't know if you can see that. I hope so. Low budget film here. So P of x is equal to h of g of f of x. I'm pretty sure you can see it here. So P prime of x is equal to the sine, h prime of g of f of x times g prime of f of x times f prime of x. Okay, so what would be a problem that looks like that? Well, we might have the sine squared of e to the x. Okay, so what's h? H is the squaring function. So therefore I would have 2 times the sine of e to the x to the first power, but we don't have to write that. Then g might be the sine function, so I would have to take the derivative of sine, which is cosine, with respect to e to the x. And e to the x is a function, and its derivative is itself. And there's the chain rule, mechanics. Right, so that was a quick 7 or 8 problems. I don't know what one we're on, I guess 7, I just saw it. So number 8, I've written number 8 over here, but I'm going to do these problems here, I believe. So let's look at the limit. As x goes to 3, that means we're looking at 2.99 and 3.001 kinds of numbers. Give us a little help. 3x minus 7, x plus 5. So now you can drop a 3 in, 2 times 8, you're near 16. Remember, we're going to be looking at numbers like 2.99, and we're going to look at 3.01, right, just to get a numerical feel. And we're dividing by x minus 3 squared. So what happens when I put 2.99 in here and 3.01? You take a moment every time I ask a question, hit the pause button, and think about things. Well, I hope you see you're going to get the same answer out. You're going to get a very small 4 digits, maybe 0.001 kind of number out. And that's fitting into, you know, maybe 15.9999 and I don't know what else, 16.001, numbers like that. Well, how many times is this going to fit into either that number or that number? I hope you say we're going to infinity. And that gives you a little feel for these things. All right, so that's number 8. Number 9, equation of a tangent line. So we're going to write the equation of the tangent line to g of x equals sine x at x equals 11 pi over 6. Okay, now if you, calculus here is easy. The hard part is, did you learn how to do that in your other classes? If not, go to the Trig playlist and look at Introduction to the Unit Circle. All right, and also, what is a radian? Very important fundamental issues here that you need to know really before you do the calculus. So 11 pi over 6. There's a circle. We're going to be drawing chunks of 6. 1, 2, 3, 4, 5, 6. We're going to go to 11. Cut to the chase. You're over here. All right, and that's going to be root 3 over 2. That's your cosine value. Minus 1/2 is your sine value in the unit circle. And you want to get good at that. All right, so what's the sine function look like? 1 period's there, 11 pi over 6 is here, and we're going up. It looks to be about 0.87, I believe. Might even be the same one we did on Friday. I don't remember. All right, so the derivative of the sine function is the cosine function, and the cosine of 11 pi over 6 we just said was root 3 over 2. X minus 11 pi over 6, that's our entry level value, that's our x1. And our y1 was, what did we say it was? Minus 1/2, I believe. Cosine, sine of 11 pi over 6, yes, minus 1/2. All right, so there's your tangent line. There's the slope of that situation here, right here. You are going up at root 3 over 2, which is about 0.87, and you're locating, well, I already have it here. So there's, I guess I just wanted to draw the tangent. There's the tangent line right there. Okay, hopefully that's believable from a numerical standpoint. So that's 9. Let's get rid of these as we go. flimsy board, but I am writing problems down over here to try to speed things up a little bit. Problem 11, equational line tangent. And we have a y of 0 equals 4. Y of 0 equals 4. So we have an initial condition here. And you find the derivative by doing dy dx equals 2xy. All right. Now, a lot of students mistake this for an integration problem. It's not. Remember, you're pausing the video each time. You've got a formula for finding slopes. It's based on x and y, and you have an x and you have a y. So it looks like if I plug 0 in, my slope is 0, which means that this line is y equals 4. Let's make this a 1. Have more fun with it. Okay? So what's the equational line tangent? Because I asked for it. Well, I need the slope, so I plug in the 1, I plug in the 4, and I multiply by 2, and I get 8. And then I can write x minus 1 plus 4, and I got the equation of the tangent. And that's coming from implicit differentiation, which we'll be doing one of today or tomorrow. And then giving you some clues as to what videos might help you understand what you're looking at. So that's number 11. Number 12 is the limit as h goes to 0 of 4 plus h cubed minus 64 over h. Now we just started diving into this the other day. All right, what you're really looking at is you're looking at a function, it's a cubic function, at 4. You get 64. Well, let's go to 6. And let's cube it. All right, 36 times 6, 216, minus 64. 216 minus 64, why am I doing this? 152, I think? Oh, God. 216, 64. We got a 2, we carry it, 5. Yeah, 152, yeah. Divided by 2 gets me 76. Okay, so if I did that, that's an average rate of change, y2 minus y1. But let's make this horizontal distance from 6 to 4. Let's make it smaller because it's going to go to 0. Yeah, let's put a 5 in. All right, so 5, that's a little easier for me. I'm trying to make this 5. Excuse me. Oh, boy, did I butcher that one. Okay, so so still 4 gets me 64. All right, let's make h equal 2. That gives me what I'm looking at, 6 to whatever it was, 152. And we said that that slope is 76. All right, let's let h go to 1. So let's put a 5 in here. Well, that's 125. And we take away 64, and we've got ourselves 6, 36, and 25. 36 and 20, 61, I think. I think we got 61. I don't know. I'm doing that on the fly. But we are moving towards a situation where we have this cubic. I'm going to extend this thing like that because I don't know how to show it otherwise. Right? We start far apart, 2 units of change, and we got an average rate of change 1 unit. We get a drawing like that. Is it believable that each time I cut this h, like for instance, I want to get 4.001 because I know that one. It's 64.04800012. 3 of these, 012001. I believe I remember that one. All right, and it looks like we're going to go to the number 48 to 1. Okay? So this was really all about, and I'm throwing things in your head at an early stage here because we're going to talk about them for a good month or so. All right, but you are looking at the derivative of x cubed at x equals 4. Just another way of writing that process. Okay? And so that's the derivative of x cubed is 3x squared. And there's your 48. Now, what would you do if you didn't recognize that? Well, you could do L'Hopital because somebody teaches you it, and you get a right answer, but that doesn't necessarily mean it's bringing you up to speed conceptually with this discipline. That's the real goal here, is to really get a deeper understanding of the mechanics, because this is the level most people drop out. They don't have a strong enough conceptual awareness of the algebra 1 through trig, and it starts to show up, those deficits starts to show up here in a big way. Okay, so I actually have to know what you're looking at. So that's what I'm seeing, and that's what I want to stress there. So let's go after it now. Problem number 13, I believe. Limit as x goes to 0 from the right. The limit as x goes to 0 from the right of 3x plus 30. We'll do it numerically. Get a feel for it. 3x squared plus 7x. Now, normally, coming out of your algebra classes, you're heading to infinity. Okay? In infinity, you look at the big players and you'd say, well, 3x over 3x squared. Well, that reduces to 3 over x. That reduces to 1 over x, excuse me. And as x gets bigger and bigger and bigger, let's put a 1 in here. Let's make it 11. Let's make it 119. Let's make it 1,900. Oh, I hope you get a sense that that's going to 0. Because we're going to infinity. In infinity, we look from right to left at the big players. We're going to 0 from the right. That means we want to look in the other direction. All right? Because what happens when you put numbers like 0.01 in there? They disappear. Right? And when I plug numbers like that in here, we're going to continue to get numbers with more zeros and a 3 at the end. And remember, if I'm going to go into this, I can do that. I can hit more and more zeros. So these are the numbers that disappear. What doesn't disappear is 30 over 7x. Okay? And what's that become if we plug in 0? Well, in this case, you could have gotten a wrong answer and been right, because that is going to infinity, right? No, I said before when we went the other direction, we were headed to 0. So excuse me, little lapse here. All right, yeah, so what happens to 7 times this? What happens to 7 times that? You get a number like 30 over 0.07. So how many times does that fit into 30? Lots. Okay, I got a little silly. Sorry. I'm allowed to get a little silly if I got myself a whiteboard and I'm doing this. Anyway, enough said. Next problem. The area from 4 to 9 square root of x dx. 4 to 9 square root of x dx. Okay, so we've got ourselves a little graph here. 0, square root always increasing. Let's call this 4. And so the square root of 4 is 2. Let's go to 9. 9 would be about here. 9, square root of 9 is 3. And we got pretty much a trapezoid there. Right? We got the width of 5 times 2 plus 3. So we're near 25 units if I did a trapezoid, which would underestimate. So our answer, oh, did I divide by 2 here? I forgot to divide by 2. My fault. So 25 halves. Okay, so we're looking at 12.5. That would be the trapezoidal area. And our area should be a little bit bigger. How much bigger? I don't know. It all depends how accurate my picture is, which I don't think is all that accurate. But first thing we do is we change that to x to the 1/2. So we add 1 to the exponent and divide. And if we add 1, we get 3 halves. And if we divide by 3 halves, then we get 2/3 x to the 3 halves from 4 to 9. Okay? Now, let's just do the fundamental theorem here. Let's drop a 9 in. The square root of 9 is 3. 3 cubed is 27. Divided by 3 is 9 times 2 is 18. The square root of 4 is 2. 2 cubed is 8. 16/3. So 16 over 3. 3 times 18 is 54/3. 44 and another 6, 38/3. And that goes in 1, 2, and 2/3 times. So we got 12 and 2/3. versus 12.5. And we said that would be a little smaller than that. So it looks pretty good. Now, proving integration actually happened a couple hundred years, I think, after Newton first put it on a piece of paper. And I believe it was Riemann, right? Riemann sum. So let's just do a quick left-hand Riemann sum. I wasn't anticipating this. 4 plus 9 is 13. So 13 halves is the distance from here to here is 13 over 2. Am I saying this right? No. Yeah, 13 over 2 is the midpoint. So 8 over 2 and 18 over 2. So 2.5 units, 2.5, that's correct now. So if I was doing a Riemann sum, I would need this altitude, and this altitude. We already have those. I don't know why I erased them. That's 2 and that's 3. But I need this altitude. So how am I going to get that altitude? I'm going to take the square root of 13 halves. And I'm going to take the square of 8 halves. I'll write it that way this time. And I'm going to take the square root of 18 halves. And in order to write this, I need that distance. And I guess we said that's 5 halves. And that would be an approximation using left-hand rectangles would look like that. I've got 2 left-hand rectangles, so I've got to get rid of that one. But haven't done this in a while. There we go. So now that wouldn't be as good an approximation, would it? No, would not be as good. That area and that area. The trapezoid would have been better. So A and B add up. But they do give us an approximation. Now what happens if we did 6 rectangles? Now let's say we did 6 left-hand rectangles. I don't know how accurate my drawing is going to be here. But I am doing more, yes? So what's happening to the area? It's disappearing. Well, what if I did billions of rectangles? If I did billions of rectangles, that little width would be really small. And that would be based on the function I'm working with. And that's the fundamental theorem of calculus. Okay? And that is a general integration. And if I want to do a direct, oh God, I'm forgetting my language now. But if I wanted to actually find a distinct value, I know that's not what it's called, I'd have to put some parameters to either create a function or an actual number. Just put some thoughts in the head. All right. I'll develop that better as we go along. I trust. Repetition is my friend. All right. So now I've got a differential equation. I want to find the area under x squared minus 5x plus 6. And actually, I'm solving for y. So this is y prime. This is dy dx. And I forgot what I actually asked. There's so many different ways to ask questions. With y of 0 equals 3. All right, so I'm giving you a derivative. How do we find the parent function? We find the area under this curve, and we've got an initial condition. So what does y equal? X to the 3 over 3 minus 5x squared over 2 plus 6x plus c. I hope I can do that without having to explain the mechanics of that at this stage. And so if we put a 0 in, boom, 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 we get 3. And that's solving a first order differential equation. All right, so our answer was x cubed over 3 minus 5x squared over 2 plus 6x plus 3. And we'll draw those pictures and we'll look at that area as we get up to speed. We'll develop a little numerical and geometric and graphical awareness. But Rome wasn't built in a day. All right. And then we got another one here. Now let's get a position function. X of t equals 3t cubed minus 2t minus 2. Okay. Now, I thought I had a different problem here, but I've got a cubic. It's basically written in graphing form. So let's actually find the point of inflection. And let's find the max values of the max and min. I don't think this video is taking quite as long as some of the others, so let's actually take some time with this. So what do I know? I know that this is 3t cubed plus 0t squared minus 2t plus minus 2. So my b is no quadratic term, and so the x value of the point of inflection without calculus now. I'm going to do this with calculus, and I'm going to do it without calculus. All right? And without calculus is much quicker. And I think I did a five cubic problems where you find the point of inflection, you find the x values of max and min, so on and so forth. I think it was one of the last videos I did before jumping into the calculus. So you can look for that practice here. So we can see that 0, right? 0 divided by 6 minus b over 3a is 0. If I plug 0 in, I'm at minus 2. So therefore, I know that I'm at this y-intercept, and I know I'm going down at 2 to 1 because this is in graphic form. And so what are the values of the local max and the min? Because it's got to look like that. Well, I have to find the value of the rate of change here, which I now know is minus 2. So I guess I'm all set. I can write 0 plus minus the square root of the opposite of, I'm going to make this a 5. I'm going to make that a 5 so that you don't see the same numbers anywhere. So now we're at 0 minus 5, and we're going down at 2 to 1. All right, I think I got to do that. All right, so from 0, I move left and right. Left moves me to the local max, right to the local min. The inverse of that slope, the opposite of that slope is positive 2. And 3 times a is 9. So it happens very quickly. Probably doesn't cross the x-axis. It probably does something more like that. All right? And those are just the x values where they occur. All right, now from a calculus standpoint, we got to do this work. We got to take the derivative, which is velocity. Derivative of position is velocity. And we also have to look at concavity. So the derivative of this is 9t squared minus 2. And we want to know where the slopes are 0. All right, so if you have a max, then right there we can see that slope is 0. And where does that happen? That happens at plus and minus 2/9, which we got from without calculus a moment ago. Okay, so now how do I know when one of the problems is a local max and one is a local min? I actually have to find a of t, which in this case is 18 times 2. Now when I put a negative number in there, negative 2/9, this is less than 0. And when the second derivative is negative, I am on a concave down interval. So that would then prove that x value. Now if I want to find the actual max and min, then I got to take those numbers, which I can't do without a calculator. I don't know the square root of 2/9. Okay? And I have to plug it in and do the work. But from a conceptual standpoint, we had the discussion that we wanted to have. All right. So now let's look at, almost done here. I don't have numbers down with what I wrote on the side. But I wrote them down to save some time. So the average rate of change of the square root of x from 0 to 25. Well, that's just algebra 1. So we have the square root of x at 0 is 0, and at 25 is 5. So what's the change y2 minus y1? x2 minus x1? That's going to be 25 divided by 5. You're going up at 5 to 1. So you started here at 0, 0. You've got the square root function. You've got your 5, 25. So that is the rate of change is 5 to 1. So there's got to be some place on the interval for the mean value theorem for derivatives, because this is continuous over the entire interval. And I can take derivatives on the open interval. I can't take the derivative at 0 and at 5, but everywhere else in between I can. And so let's take the derivative, the square root of x. 1 over 2 root x, I ask you to memorize that. And we want that to equal 5. Okay, so that's 1 equals 10 times the square root of x. So, wow, we're really going up at 5 to 1 very quickly here. very quickly, near zero. Wow. So it's the square root of 1/10. Now, yeah, I don't want to get talking about plus minuses or anything else. So it happens very quickly here. And that is surprising to me. Although I know that the square root of x, boom, because it's the inverse of x squared. So yeah, that makes some sense. Makes some sense that it would happen that quickly. All right. Unless I made a mistake, and I got Yasser there. I heard from Yasser the other day, this morning. So I got backup. All right. Because when I get to the end of the videos, we know what happens. All right, two more problems. 2x squared, x minus 5, x plus 3. 2x squared, x minus 5, x plus 3. And we're going to call that f prime, little f prime. And we want to know when f, little f, is increasing. When is little f increasing? Well, little f is increasing when tangents are positive. Okay, if a tangent is negative, it means the function is decreasing. So we're going to make when this thing is greater than 0. And I'm going to continue to do it graphically. Oops, stepped on something here. That wasn't fun. I'm going to continue doing it graphically so I can look at -3, sign change at -3, odd exponent, 5, sign change there, odd exponent, no sign change at 0. Right? I know when I put a big number in, I get a big number out with a sign change, no sign change, sign change. So it's going to look something like that. And so when is this positive? It's positive from -infinity to -3, union 5 to infinity. So we had ourselves a 4th degree polynomial. We're going to end up with a 5th degree polynomial, one jump up, and 5th degree polynomial might look something like that, yes? Increasing, increasing, increasing. It could look like a cubic. Increasing, decreasing, could look like that. All right, but at the left side and the right side, we're definitely going up. Left side and right side. Okay. Last problem. We're going to integrate. We're going to start with a y prime. Y prime. Let's start with y equals. Y equals 2x, x squared, e to the m dm. Okay? So once we start playing with this, it's a 3-second question. You just write your answer. Seeing y, we got to chip away at it. So let's actually look at this integration, because then we can take a derivative and see what it is. So e to the m is itself. We often refer to these as dummy variables because I'm going to turn this into a function in terms of x. Doesn't matter what letter I use. I'm plugging x squared in, so y could have been written as e to the x squared minus e to the 2x. Now we've done this derivative, right? We've done chain rule. So if I wanted y prime, I have e to the x squared, and I have to multiply that times the derivative of x squared, which is 2x, minus e to the 2x times 2, for the same reason. I'll put a little line there. Okay? Well, could you get here from this without having to do that? Because if you can find the rate of functions that don't even have the ability to be integrated. But you can still tell how you're changing in an instant. Very powerful moment here. So, e to the x squared, where could I get that? Boy, what would happen if I dropped x squared into m? It's exactly what I did. And then what do I have to do? I take the derivative of what I drop in. Well, there it is. So, same thing. I got to drop 2x into the e function. Okay, I did. And I got to take the derivative of what I dropped in. I guess we can start doing problems like that and build off. Now, did I catch every problem I wanted to do? Good enough. All right, good enough. Good enough practice for the day. And I hope these videos come out. I'll upload it and take a look before I make it public. And trying to get the lighting right. Trying to see if it captures this in a way that I can keep showing it to you. Alrighty? And then I'll do the second half of this worksheet. Now, worksheets in my class, students go to the boards, and I walk around the room, and if I find somebody that knows how to do a problem, I tell Sally to help John. You know, and then until somebody can help somebody else, I run around quite fast. But as soon as somebody knows how to do a problem, we start playing tag. And the last stage of learning is explaining something to someone else. So I'm afraid you've got to go find somebody else to explain this to. Maybe you're in a class. Maybe you're doing this kind of work. And maybe this helps. And if you get a chance to help your neighbor, please do. Because it not only helps the other person, it's just good citizenship, but it's going to help you. All right. There's my little 2 cents. And this is 40 minutes long. Don't want it to be any longer than that. All right. Do it again tomorrow.